Good morning, Professor Chikano and TA. Today I would like to share about my project to you. My project is about azo dye aligning layers of liquid crystal. And then I will go through a few parts of it. First, I will talk about the general synthesis of azo dyes. Then next, I will talk about the mechanism of photo orientation process and measure of orientation of azo dye. And later on, I will give some examples of different types of LCD using different azo dyes. First, this is a general synthesis of azo dyes. After adding some acids into this substance, then it will become like this, and then we will add another acid to become our desired azo dye. And here it is shown over copulation. It will be formed as secondary product, or if P position occupied. Next, Next, I would like to show you the mechanism of the photo orientation process. Gravitational diffusion will occur in thin solid layers. UV light induces an symmetric potential field when the dye absorption oscillator is perpendicular to the induced light polarization. Here, this is the absorption oscillator, and we call azo dye chromophore. And this arrow shows the long axis along the azo dyes. The azo dye will exposure to the UV light and align to be perpendicular to the direction of UV light like this. And this is what we call equilibrium position. The reason for the oscillator reorientate perpendicular to the direction of polarization is the azo dye molecule will take up a proton to increase their energy and cause them to reorient. Photo alignment could take place in monolayers of azo dyes, in polymer materials containing azo dyes, liquid crystal materials, a point-oriented layer of azo dyes, and in liquid crystal solution of azo dyes. The reoriented azo dye layer is able to reorient again by the UV radiation. The polymerization of azo dye materials can increase the thermal and UV stability. You can see that this is the original azo dye. After polymerization, it will become like this. And here we can see that this is some commonly used azo dyes. We have SD1, CD1, EY, CDY, DR223, and infrared. We can see that they have different structure, and F filter will be used for measure the distribution of orientation of the molecules, where theta is the angle between the molecular axis and the direction of the light polarization. At the initial state, F will equal to 1/4 pi, and the final desired state will become like this. The distribution can be related to the anisotropic dichroism, or by reflections of the photo alignment film. Dichroism is related to S theta and also order parameter. Order parameter is proportional to the azo dichroic ratio R. And here is two formulas showing that how we can calculate the dichroic ratio and order parameter. The dichroic ratio will be high if the oscillator direction is parallel or perpendicular to the long axis of molecule. This is the absorbent substrate of the azo dye. And here we have measured the curve ratio and other parameter of different types of azo dyes. And now I would like to give you some examples of different LCD. First, VAN LCD. We will use the in-situ photo alignment method which can vary the pre-tau angle from the homotropic direction. PI will be used for homotropic alignment in a combination with azo dye. If you use PI only, the pre-tau angle will be 1.4 degree. But if we mix it with SDA2, the pre-tau angle can be increased to 2 to 3 degree. And the next example is twisted pneumatic TN LCD. Plastic substrates use azo dye photo alignment layers. We'll use double exposure method. Super thin azo dye SD1 will be used because it has high asymmetrical and correct energy, which is larger than 10 to the power negative 4 joule per meter square. We'll mix it with SDA2 to make the pre-tau angle larger, and it will become around 5 degrees. And recently we have the new photo aligned TN LCD cell. One-step illumination with oblique non-polarized UV light of an empty cell with azo dye layers coated on ITO substrate. If the incident angle was sufficiently large, which means that larger than 75 degrees, the photo alignment of the azo dye layer on the bottom substrate become perpendicular to that of the upper one. And also, LC directors on the top and bottom substrate will orient perpendicularly. Plastic full-color TN LCD can be produced using the photo-aligned polymerized azo dye film SDA2. LC alignment on a plastic substrate is possible under continuous process, such as roll and to-roll technology. The last example is ORW TN LCD. Optical rewritable TN LCD shows a high contrast and a long lifetime. SD1 can be reversibly change the orientation in the plane of the substrate, while the other substrate keeps a strong asymmetrical and correct energy. In the dark state, the twist angle will be 0, but in the bright state that is totally different. It is exact around 90 degrees between two crossed polarization with a special mask to create the image. Asymmetrical and correct energy and the apparent twist angle are proportional to the intensity of UV light passed through the mask. Any gray level can be realized depending on the different energy and the pre-tau angle. SD1 can change its alignment reversibly without any photochemical. That means it can erase and write the image anytime you like. The sensitivity of new SD1 is greatly improved to around elec520 mJ/cm². That means it can erase and write the image in several seconds, which is very fast. I hope that you have a good knowledge of my project after my presentation. Thank you very much for your attention.